This is the AP Chemistry lecture for oxidizing and reducing agents that we went over in class on Thursday and Friday. And this will be on your test, so you do want to make sure that you go over this. This PowerPoint is uploaded, so you can print off the PowerPoint and look on as I go through it. But you want to make sure maybe you either copy it or at least read it. So this is continuation of electrochemistry. We've talked about oxidizing and reducing agents before. Now we're going to relate those to voltage. The more positive the voltage, which we call reduction potential, which means its potential to be reduced, the more likely the substance is to be reduced. This is also going to make it a stronger oxidizing agent. The word that the book uses for oxidizing agent, they actually call it an oxidant. So basically they'll run those two words together. Oxidizing agent and the word oxidant mean the same thing. So the more positive your voltage, the stronger the oxidant is. That would be the reactant, and it's more likely to be reduced. And then the opposite of that, the more negative the reduction potential, the more likely the substance is to be oxidized rather than be reduced. And this is going to be a stronger reducing agent, and the term that we sometimes use in the book is called a reductant. So there is a worksheet that goes with this, and those types of questions that are on the worksheet will be the types of questions you will see on your test. So what we did in class, the very next slide, has the chart that I gave you guys when you took your quiz, so you should have a copy of this. If not, you can print this off and you would have another copy of it. This is a reduction chart. You know it's a reduction chart because all the E's are over here on the left. They're all starting as ions and they're making solids. When we talked about the metals, we were talking about a few nonmetals, then they're starting out as element form and they're actually going to ion form. So because it's a reduction chart, everything's being reduced. And if you look, the highest voltage here is going to be the one that is most likely to be reduced. And the one that is most likely to be reduced on this chart is fluorine. Fluorine gas, it's right here, is most likely to be reduced. And the reason we know that, it has the highest voltage. So if I were to label him, kind of like if you were labeling somebody in class most likely to succeed, this guy is the most likely to be reduced. And that increases as we go up. It's not a very straight line, but as we go up, this one is so much more likely to be reduced than lithium. If you look, lithium is actually a negative here, so lithium ions don't like to be reduced to lithium solid. That's why we find lithium don't find lithium very often, not in ion form. He doesn't like to be in a solid form. So these are least likely to be reduced. So least likely down here, most likely up the top. Now if we think of this the way we're written, if this is being reduced, then this would be labeled as an oxidizing agent. So up here we would have the strongest oxidizing agent, also known as an oxidant. Down here we would have the weakest oxidizing agent. So if I ask who's the stronger oxidizing agent between copper 2 and zinc, well, he's up higher in the chart. He is a stronger oxidizing agent. Copper 2 is. Then there's some questions on the worksheet about, well, is it weak or strong? And here's our division line. Our division line is right here at the hydrogen. All the guys that are negative are actually weak oxidizing agents. All the guys that are positive are actually strong oxidizing agents, or actually strong oxidants or weak oxidants. So that's how you know, depending on if they're negative here or they're positive. So hopefully that makes sense to you as far as most likely to be reduced, or strongest oxidizing agent, or weakest oxidizing agent. Now we're going to get a little confusing because when I used to teach this and I had my overhead projector, I could actually take this transparency, because I had this little thing on a transparency, and I could flip it over. And when I flip it over, they're no longer reducing equations are actually oxidizing equations. And so if you flip it, so now we would have this guy written over here and these guys written over here. When you do that, all your charges actually become negative up here and positive down here. So now you have to think in flip mode, because unfortunately they don't make an oxidizing chart. They expect you just to be able to read this chart as an oxidizing chart. So now if we think of it as flipped, a flipped chart, I'm going to write flipped up here. Okay, when flipped, these guys would all be negative, and these guys would now be over on the reactant side, these would be on the product, and these would be oxidized. So therefore, since these are going to be negative, these are going to be the least likely to be oxidized. And down here, if we were to flip those, we're talking about lithium as our reactant, that would be most likely. My pen is not working very well because I'm sitting so close to the Bluetooth. Most likely to be oxidized. So now, again, we're still thinking of them as flipped. If they're flipped, if it's going to be oxidized, this would actually be a strong reducing agent. So our strongest reducing agent is actually lithium solid, and the strength increases as we go down. Again, not a straight line. Sorry about that. So the type of questions that are on the worksheet would be something like this. If I gave you Cl2, and I said, is Cl2 a strong oxidant, weak oxidant, a strong reducing agent, or a weak reducing agent? Well, since he's over here on this side, he's actually a strong oxidizing agent. And we got a knock on the door, so hold just a second. Okay, we are back. Sorry about that. So that would be the types of questions. So now if I gave you like silver solid and I asked the same questions, would it be a weak oxidant, strong oxidant, weak reduction agent, or a strong reduction agent? Well, since he's over here, and if we were to flip him around, he would actually be being oxidized, and he would be a weak reducing agent. So over here are going to be reducing agents if I give you one of those. Over here, if I give you one of those, they're going to be oxidizing agents. Up here are the strong oxidizing agents. Down here are the weak oxidizing agents. Over here are the strong reducing agents. Up here are the weak reducing agents. And if you can learn that, you can answer all the questions that would come on the test from that. So again, there is a worksheet. It is attached on Edmodo, or if you were absent, you can come by and get that from me. So don't wait till the last minute, because that is on the test. Our next thing is something called Gibbs free energy. Now we're actually going to learn more about Gibbs free energy later when we talk about thermodynamics and we talking about thermochemistry. But since we're talking about voltage, there is an equation that relates it to voltage, so we're going to go ahead and do Gibbs because it's kind of easy. And then later when we do thermochemistry again, I'll say, remember we did Gibbs with voltage, and then we'll come back and look at this equation again. So what you kind of need to know, if it's negative free energy, means that the reaction is going to be spontaneous, and that E's are related by the following equation. And here's our equation that we're going to be dealing with. Delta G stands for, delta means the change in, G means Gibbs free energy. Then it's a negative. N is going to stand for the number of electrons that are going to be passed. F stands for Faraday's constant. And E is actually voltage. And that's actually all the stuff is on the next slide. Again, you can print these slides off and you can have these. So this is what everything stands for. I'd like you to show you something. Do you see this right here? Gibbs is actually measured in kilojoules per mole. But unfortunately, Faraday's constant is, and that is a time sign, so it's actually a joule/volt times a mole. It looks like that. When I multiply these numbers together, the unit actually comes out in joules per mole. And so you're going to have to divide by 1,000 in the end to make this work. I don't know why they don't just give the constant this way. And we're just going to use this constant because that's the same one you're using with your electrolysis. So that way you can already remember this constant is 96,500. So we're going to work one of the problems. If you pull up the PowerPoint that I uploaded this PowerPoint yesterday, and I have changed the example problem. So to make it a little bit simpler, this will probably be one like you will have on your test. It says, what is the Gibbs free energy for a reaction of copper 2 nitrate with sodium metal? And it wants to know if this reaction is spontaneous or not. Well, the first thing we would want to do would be write the equation. So you've got copper 2 nitrate, and we're reacting it with sodium metal. And we've got a single displacement reaction, so it definitely is a redox. Single displacements are redoxes. And so sodium is going to hook up with nitrate, and poor little copper is going to be left all by himself. It doesn't have a 2 with it because it's just a solid piece of copper. Now, if you will do net onyx, it will make this a lot easier. Hopefully you can see we're going to slash this because we slash all nitrates. We slash them, we put their charges. Technically, we label them aqueous. This is a piece of metal, so he gets boxed, no charge on him. He is a solid. This is aqueous because of that nitrate again, and this is a piece of metal labeled solid, no charges. So if we get rid of our spectators here, our spectator again is nitrate, my favorite. So we could say, well, we really got some copper ions reacting with some solid sodium. Going to make us some sodium ions, going to give us some solid copper. So there is our redox reaction. You can see copper going from a 2 to a 0, and sodium going from a 0 to a +1. So we're going to want to break this into half reactions and balance it. You could have balanced it up here, but I want to do half reactions because we need to see the electrons. And half reactions are where we see the electrons. So this guy is going to match up to this guy. We're going to put 2 E's over here on the reactant side. This is a oxidation or reduction. This is a reduction because my E's are over here on the reactant side. And then we've got sodium, going to go to sodium ions. And then we're going to have only 1 E here. Now, we want those E's to cancel out for the overall reaction. So in order to do that, we need to run a 2 through this equation. Now, if I rewrote this, you would actually see those E's canceling. It's going to be real important for that to happen. This is very much like your lab where you make those E's go away. Alright. So there's my equation. Now we could actually look on the chart and find the voltage. And so if we looked on our chart for copper 2 going to copper solid, this actually makes a positive 34 volts. This is just like he is in the chart. This guy is flipped because he is being oxidized. So if we look on our chart, we will find on the chart it's a negative 2.7, so we flip him around, it's a positive 2.71 volts. And I'm simply going to add those together, and that's going to make 3.05 volts. So that's good. Is this spontaneous or not? It's spontaneous because we have a positive voltage. So you can actually tell if something's spontaneous or not by just looking at the voltage. But we're going to put him in Gibbs free energy just so we can see how that formula works. Delta G equals negative N times Faraday's constant times the voltage. The little circles just mean they're at normal standard conditions. We've got a negative. The N stands for the number of electrons. That's why we needed to have, it's not 4, it's 2. 2's giving and 2's taking. So it's a total, like if I were giving someone a quarter, I would give up a quarter and they would take the quarter. That wasn't 2 quarters, that's just 1 quarter. It's a give and a take. There so happens to be 2 here, so this is 2. Faraday's constant is 96,500. That should look very familiar. The unit we're going to use is joules per volt times mole. And then we're going to have our voltage, which is 3.05 volts. And we're just going to multiply those together. And let me get my calculator because I don't have this written down. -2 times 96,500 times 3.05. Get a really large number as 588,650. If we'll look at some units canceling, volts is going to cancel. You're going to be left with a joule per mole. But Gibbs is actually measured in kilojoules, and so you actually have to divide this answer by 1,000. So you're going to end up getting, if we do 3 sig digs, because I'm kind of fond of 3 sig digs, you're going to get a negative 589 kilojoules per mole of free energy. Negative means it's spontaneous. So, two things can tell us it's spontaneous: a negative G or a positive voltage. And the reason that works is because there's a negative sign hanging out here. So if this had been negative and non-spontaneous, the negative and the negative would have made a positive, and Gibbs would have been positive. So Gibbs and voltage are like opposite as far as sign, as far as spontaneity is concerned. And that is your full lesson. There is one of these on the worksheet. There'll probably be just one of these on the test. It's not that hard. I figure since we were going ahead and using Faraday's constant with those other problems, we were already calculating voltage. All we needed to add was to figure out the number of electrons. And we have to remember to divide by 1,000 just because of the unit difference. A lot of books might use, they divide by 1,000 here. They use 96.5 kilojoules per mole Kelvin, but really Faraday's constant is 96,500. So, and that's what we use for 1 mole of electrons. So it works just to go ahead and do it there and divide by 1,000 at the end.
The last part of today's lesson is known as the Nernst equation. The Nernst equation is used when our voltaic cell is not at a standard condition. When I mean not standard, when we've been putting the little degree sign, which is called the E naught. The E naught means at standard conditions, which we're assuming that our concentration of our solutions that we're dipped in, that our metals are dipped into in our voltaic cell, is at 1 molar. So if we're not at 1 molar, it does affect the voltage somewhat. Not a huge amount. We're not going to see a huge amount of voltage change, but it does cause a shift either to the reactant side or product side. It is Le Chatelier's principle going on. And the other standard is at 25 degrees Celsius. We're not going to look at what if we were to change the temperature. There is a variation of this Nernst equation if you were to change the temperature, but we're just going to still stay at 25 degrees, and we're just going to change the concentration and see what would happen. So this is the equation that you're looking at. So this is standard conditions called E naught, and that's what we've been calculating when we flip one of the sides and we add those voltages together. We've been calculating what we call standard cell potential or standard voltage. Okay, so that's going to be normal. And then we're going to subtract, this is the 0.0592, and that number comes from manipulation of the formula between Faraday's constant and temperature, a few things going on. So we'll just use that as a constant divided by n, and that is the number of electrons. This is number of electrons that are going to be being exchanged in the chemical reaction. N always is the number of electrons, just as we saw before. Okay, so number of electrons is our N. And then it's the log of Q. Alright, we've got to dig back into equilibrium. Remember, the equilibrium constant K was after equilibrium was established, but Q was called the reaction quotient, and it worked just like K, except you got to use initial amounts. So to calculate Q, it is going to be the products over the reactants, and it's raised to their coefficient power. So we are going to raise those to the coefficient power. So this is relating back to equilibrium somewhat. And what we don't put in there are solids or pure liquids. And we're going to see some pure liquids, not aqueous. Aqueous does go in there. Okay, so we're going to see those solids not play a part, but we're going to see those molarities of those solutions play a part. All right, so we're going to do 3 sample problems of this and just see how changing the molarity not at 1 molar, how it would affect. And so this is our problem that we're going to work with. I said 3 problems, there's technically 4. So we're going to calculate the standard cell potential if we were at normal conditions. And it says calculate the standard cell potential for a voltaic cell, meaning we want a positive voltage, created with aluminum in aluminum nitrate and copper in copper 2 nitrate. Okay, so we're going to do that first. And once we have that variable, we're going to then see what would happen under these 3 conditions here. So if you want to, I did put this PowerPoint up so you can either print it off or you can just write with me. We're going to do the first one. So I'm going to scoot down and then we're going to address the situation. So we'll be coming back up. All right. So the first thing is we need to figure out what that reaction is. So nitrates, again, those are spectators, so we're not really going to worry about the nitrate. So I'm going to figure out which way this cell is going to be going. So I know aluminum is a 3+. And so I would find, let me go ahead and get those, let me get those states of matter on there, because it really is going to matter when we do this. So we do that, and I'm going to go ahead and do that copper. Now right now I'm just writing these down to see which one is going to get flipped. Remember, I'm just pulling this from that chart, and I'm doing this so that we can review this. If I pull this from the chart, I will see this is a negative 1.66 volts, and I will see that this is a positive 0.34 volts. Alright, you can already see by looking at this that this one's going to stay being reduced, but this one's going to need to be flipped around, meaning that this one is a reduction. It's most likely to be reduced, and that is a strong oxidizing agent or oxidant there. Okay, this one's going to need to be flipped around for our equation. So I'm going to take advantage of the fact that that one's already there, and I'm going to go ahead and flip this guy so that we can see. And so we're going to have this solid, oh, I forgot to put aqueous in there. And we've got those. So I'm going to go ahead and flip that. Pen is being a little ornery this morning. Alright, change that sign to a positive 1.66 volts. Let me get that other guy erased up there. Alright, so this is kind of just reviewing everything we've talked about. We are doing voltaic, so I flipped it so that we're going to get a positive. So we're going to get a 2 volts in this reaction. Let's just kind of review this. So my E's are over on the reactant side, so this is reduction. So this would be my cathode. Cathode always gains weight. This would be my oxidation. And so this would be my anode. And again, anodes always lose their mass. The electrodes is what I'm referring to. So that's just a review of all that. If we could draw it out and all that good stuff. And so this one, again, the electrode would have a positive. This one would have a negative. Electrons always flow from the anode to the cathode. Just to review all that. So if we wanted to balance these E's out, we got 2 here and 3 here. So you would need to multiply the top equation by 3. So we're going to get a 3 here, a 6 here, a 3 here. I need to do this because I need to figure out how many electrons. And then the bottom equation is going to multiply by 2. And then I bring them together. So let's bring them together in purple. So 3 copper 2 aqueous plus 2 aluminum solids going to yield 3 copper solids plus 2 aluminums 3+. Alright, so when I calculated this, this was at standard condition. That's E naught, they say. So E with the little degree sign. So that's the standard condition. So 2 volt is the answer to that first question. I'm going to do one more thing. I just want to review that cell notation with you while we're in the middle of this one. It's always good to keep reviewing. So I had the anode. Anode would get written first, and so it would look like this. And I would put a slash, and again, sometimes they don't put the coefficients in there, so I'm just doing it for emphasis here. On Chem 101, on the Nernst equation, which is what we're doing, they'll use your cell notation, and then they will be putting, they're changing the solution. So just know the anode is always first, and so this reactant, this is technically the yield sign, and then your product, so it's always anode. And then they're separated by that salt bridge, and then you have your cathode reactant slash your product. And so I just wanted to review you on that. So this is the anode, and this is the cathode. Okay, reactant, product, reactant, product. That's the way a cell notation looks. All right. So now, that's old lesson. So now let's look at new lesson. So we are going to now change, we're going to do A first. We're going to change the concentration of our solutions. And so if you'll notice, standard conditions is 1 mole over everyone. So not really changing the copper, I'm changing the aluminum. And I'm actually making the aluminum twice the molarity. Okay, so the aluminum ion is going to be twice. Now, I'm going to get that cell notation out of there just for space. Do you see where the aluminum ions are? The aluminum ions are located on the product side. According to La Chatillier's principle, if you increase on the product side, it's going to cause it to shift this direction. So if I increase the product, I'm going to see the voltage go down because the reaction is going to shift more that direction. So increasing the product is going to lower the voltage. Does that make sense? Okay, if I increase the reactant, I'm going to see the voltage increase. So if I increase this guy, I'm going to shift it this way. Voltage is going to get a little bit bigger, not a huge amount. And if I increase the product, it's going to shift that direction. You're going to see that voltage go down because this is that forward reaction making that voltage. Hopefully that makes sense. That's a review of La Chatillier's principle. We got lots of things to review in here. Same thing going on. If I decrease the concentration of this, well, remember, if you decrease a product, the reaction is going to go more that direction. It's kind of like if you make a hole, you got to fill it. So if I lower the concentration here, the reaction is actually going to shift more that way, and we're going to see that voltage go up. Weird. Same thing here. If I lower the concentration here, the reaction is going to shift that direction. We're going to see that voltage go down. So it is La Chatillier's shifting going on. We are going to use the Nernst equation for that. So let's write that Nernst equation here so that we can see it. So we are looking for the E not at standard condition, so the little naught is gone. And we're going to use the E naught, and we're going to subtract from that 0.0592 divided by our moles of electrons, which is moles of electrons, and that's going to be multiplied by the log of Q. So the first order of business is to find Q, because all this rest we could just plug in. It's going to be easy. So we're going to find Q first. And so again, Q is the products over the reactants, not looking at the solids. So this guy's a solid, so I'm not going to look at you. This guy's a solid, so I'm not going to look at you. Okay? Remember when we did K, you weren't supposed to ignore solids and liquids, so we're not going to look at that. So I'm going to be looking at products, so of aluminum ions, and they're going to be raised to that second power divided by the copper ions concentration raised to the third power. So this is going to say true for all of our examples. So I'm not going to erase that. I'm just going to plug into that. All right, so our first example, example A, has us changing our concentration of, I've already forgot. Let's go look up. Not wanting to go up with me. Has us changing aluminum and not changing copper. So we're going to change aluminum and not change copper. And we are changing that aluminum to 2 molar. 2 molar. So our aluminum concentration is going to be 2 molar, but it is getting squared, divided by 1 molar cubed. So 1 cubed is just 1, 2 squared, so you're going to get 4 there. So I need to be taking the log of 4. So for A, I'm going to figure out E equals, the E naught we just found was 2 volts, okay, minus 0.0592 divided by moles of electrons. Our moles of electrons, some of you are missing this on your quizzes. There are not 2 electrons, there's not 3 electrons, there are 6 electrons. There's not 12 electrons. Okay, someone is gaining 6 electrons, the other one is losing 6 electrons. It is a give and take of the same amount. So the number of electrons in total is 6. 6 electrons there. And then we have log of 4. Alright, you should be able to put that in the calculator just like that. I would tell you to try to make sure you get the right answer. When you put this in the calculator, we already said that we are increasing this guy, so we're going to see the voltage, we're going to see it shift to the left, so the voltage is going to go down. I'm sorry, but it does not go down much. It's going to get a 1.99 volts, but it does go down. So there's A. Alright. Now we're going to go B. So B, we're going to figure out Q first. I would always recommend that. And it's aluminum over copper. And so if I go back up and look at the aluminum we left at 1 and the copper we moved to 3. So 1 for the aluminum, which is on top, squared, and we change that one to 3, but it is cubed. So basically I have 1 over 27 here, 1 over 27. You could calculate that out, or you can leave it like that. If you calculate it out, you get 0.037037. Sometimes it's easier just keep it in the calculator rolling. Alright, when we solve it, we get E equals 2 volts minus 0.0592 divided by 6, again, same problem, log of the 0.037037, etc. And we are going to see the voltage. Oh, what do? We increased the product, so we should get a higher voltage, and unfortunately, it's not a huge amount of difference. So we should be getting that. Alright, hopefully that's not bad. Letter C. Chem 101's got some good questions. So letter C, we are going to change both of them, and we're going to see how that's going to roll. So we're going to change the aluminum to 0.01, and we're going to change. So aluminum's going to go pretty far down and copper pretty far up. So we're going to hopefully see a voltage. So aluminum's going to go down, aluminum going to go down, copper's going to go way back up. And let's see how that affects that. So aluminum we changed to 0.01, and that is squared. And the copper we changed to 6, and that is cubed. And I just put that in the calculator. I did not square it, write it down, cube it, write it down, whatever you want to do. And I'm just going to use 3 sig digs here because It's not going to make a huge amount of difference. 4.63 times 10 to that is a -7 that we got there. -7 there. Alright, last thing, 2 volts, left off of volts there, minus 0.0592 divided by 6 log of 4.63 times 10 to the -7. And so, if I put that, you would think, making that so high and that so low, that you would get a huge difference in voltage. You get 2.06, I think, volts is what I got. Not a huge amount of difference there. You can get much bigger differences depending on how big variation you get. Alright, that is pretty much the Nernst equation. So hopefully this makes sense. Please email me if you need help in any way.